Hey everyone, welcome to this explainer. Today, we're diving into something totally mind-bending, the biopolitics and materiality of the script. We interact with our devices all day long, kind of just assuming our data magically floats around in this invisible digital ether. But what if we completely shattered that illusion? That's exactly our goal today. We're going to dig into the source material to uncover the harsh physical and surprisingly biological realities hiding behind computer code.
Okay, let's dive right into our roadmap for today. First up, the myth of immaterial software. Second, the bold claim that there is no software. Third, the materiality of storage. Fourth, DNA as an active script. And finally, the politics of programmability. Let's get started.
Section 1. The myth of immaterial software. Okay, I want you to really think about this for a second. When you press a key on your keyboard, why does a letter actually appear on your screen? It's something we do, thousands of times a day without even blinking. But when you stop and think about it, we just automatically assume software is this invisible, floating force that simply wills those letters into existence. Media theorist Wendy Hu Kyung-chun actually has a brilliant, playful term for this. She calls it sorcery, spelled with an O-U-R, like source code. It's the illusion that source code is a form of magical writing. We type a command, hit enter, and poof, magic happens. We literally treat ourselves like wizards casting spells. We even scream at a frozen computer like it's a sentient being, right? We completely forget that code is really just a set of physical instructions grinding away inside a machine. Which brings us to Section 2. There is no software. There is no software. Wow. That is a famous, highly provocative claim from German media theorist Friedrich Kittler. And it completely pulls the floor out from under everything we just talked about. It really forces us to look past the cozy, user-friendly interfaces we're all so used to. And this brilliantly illustrates the divide we're talking about. On one hand, we have our everyday illusion, code as this abstract, magical text just floating in the cloud. But Kittler's reality, it's entirely different. Code is, at its absolute base level, just local string manipulations and microscopic voltage differences. All those apps you love using, they're ultimately just physical, electrical charges turning on and off in a piece of silicon. Looking at Kittler's original argument here, you can trace this descent from high-level software abstractions straight down into the bare silicon. He argues that high-level programming languages are really just obscuring the hardware. We might type metaphorical commands like call or return, but at the end of the day, it all boils down to signifiers of voltage differences. Software is essentially just a user interface masking a purely electrical event. All right, Section 3, the materiality of storage. So how do we wrap our heads around this physical reality? Scholar Matthew Kirschenbaum gives us a super helpful mental model by breaking this down into forensic and formal materiality. Forensic materiality is the physical wear and tear. It's the tangible stuff, what literally shatters when you drop your hard drive, or the toxic e-waste sitting in a landfill. Formal materiality, on the other hand, is the computer's simulation of materiality through programmed states. So your hardware has this harsh, undeniable physical reality, but your software? It's only ever simulating it. And this brings us to what Kittler calls the price of programmability. You see, programmability isn't just some abstract floating feature of software. It's dictated entirely by physical constraints. Whether we're talking about an old telegraph relay or a modern silicon chip acting as a controllable resistor, the ability to compute is an exclusive feature of the hardware. We actually have to chop up continuous algorithms into discrete, tiny pieces just so they physically fit onto the device. Now, what's really interesting about this is how these physical constraints directly intersect with power and control. Take the Intel 8286 chip, for example. It featured a protected mode that literally embedded military-style privilege levels straight into the hardware itself. Why? To physically keep user applications away from the operating system's core. So power and access control aren't just software rules. Actually, scratch that. They aren't software at all. They are quite literally inscribed right into the architecture of the chip. Moving right along to Section 4, DNA as an active script. Now, this brings up a really profound question from our sources. If computer software really just boils down to hardware voltage, where in the world did we even get the concept of an active, programmable code in the first place? Well, as it turns out, the answer doesn't come from computer science. Let's see how this builds. Because according to Wendy Hui Kyung-chun's historical findings, the logic of a programmable script actually originated in biology. Look at this timeline.
It starts way back with Mendelian genetics in the 1860s, introducing genes as this active script that determines form. This then influenced the practices of eugenics and breeding in the early 1900s. Jump to the 1940s, and this biological concept heavily influenced cybernetics. And that laid the direct groundwork for modern digital computer code in the 1970s. So the conceptual blueprint for your computer's code was actually DNA. Mind-blowing, right?
To really grasp this idea of biological computation, let's look at Dennis Bray's example of the amoeba, or what we can call wetware. An amoeba is a single-cell organism. It has absolutely no brain, no nervous system, nothing like that. Yet, its biochemical networks function as a form of non-silicon computation. The way it grows and divides is a form of active decision-making. It produces deliberate cellular variations to anticipate future environmental changes. It's living proof that computation and programmability exist organically in nature, without a single silicon chip in sight. And finally, Section 5, the politics of programmability. So Chun points out a unifying logic tying all of this together. Programmability, whether it's happening inside our biological DNA or inside our silicon chips, is fundamentally the logic of anticipating, commanding, and controlling the future. From an analytical standpoint, she links the history of computing to modern governance, noting how software is increasingly used to extrapolate data patterns from our past to pilot and control our future behavior. It becomes this incredibly powerful tool for societal management. Which leaves us with this final lingering thought. If both our DNA and our computer code are programmable scripts designed to anticipate and control outcomes, who or what is programming the future? It's a profound question, isn't it? One that completely shatters that illusion of the digital cloud, grounding our technology right back into the physical circuitry of the Earth and the biological realities of our own bodies. I really hope this explainer leaves you with a totally new perspective on the machines you use every single day. Thanks so much for learning with us, and keep questioning the systems around you.